Okay, thank you everybody for joining us for two more excellent talks as part of the JETZON Ocean Decade program. Getting quickly started, our first speaker is Martha Gledhill from GMR, who's going to talk to us about controls on ion distributions in the subsurface South Pacific. Over to you, Martha. Thank you.
Okay, thanks, Adrian, and thanks very much for inviting me to give this talk. And I hope you can see my presentation.
Yep,
Okay, excellent, and everybody can hear me as well, I
yep.
gather. Yeah, so I'm going to talk today about chemical controls on ion distributions in the South Pacific Ocean. So this is work that we just published in Nature Communications a few weeks ago, and that was done as part of the GeoTracers program with funding from the German Ministry of Research and Technology, and in collaboration with a whole bunch of people, including the co-authors, which are all mentioned here on the title page. So I think I don't really need to emphasize why iron is an interesting element to work on. We need to understand iron because it's a limiting nutrient in the ocean, and so we need to kind of understand what controls iron distributions. And I think, this is a good schematic on the overall controls from Al Tagliabue's work from 2017. And it shows, that iron is influenced by sources from margin sediments, from atmospheric dust, and from inputs from the deep ocean as well, from hydrothermal vents and sedimentary inputs from the deep ocean. And then once iron gets into the ocean in the surface, there's some microbial uptake by phytoplankton. That occurs as part of photosynthesis. So as organic matter is produced in the surface, then iron is taken into that organic matter just because it's a required nutrient. And then as this organic matter sinks into the deeper ocean, which is the part that we're interested in this talk, then we start to get other processes which can influence iron biogeochemistry. And this is where the decoupling of iron cycles really from nitrogen and phosphorus cycles becomes more important because iron is not fixed to carbon in the same way that nitrogen and phosphorus are. It's ionically bound to organic compounds, and so you have the influence of chemistry then. So this is where chemistry comes into play. And we have to understand this in order to be able to understand why iron has such a short residence time in the ocean and what the factors are that control that residence time and therefore control the overall iron inventory. So these are the things that I'm going to concentrate on in this talk. So this talk is really about the iron scavenging and release and this organic matter, which is often called ligands in the literature, and how this organic matter influences this iron biogeochemistry and sets the amount of iron inventory in the ocean. So drilling down into this a little bit more deeper, this is our current conceptualization of chemical controls on iron in the subsurface ocean. Sorry, so we're away from the photic zone, so I don't have to think about redox chemistry too hard, and we're in the deep ocean where we don't have too much in the way of biological productivity or hopefully not too much respiration as well. Although we'll see from the next talk whether that's the case, and we can just think a little bit more about the abiotic processes which are occurring here. So we've got this ligand binding over here, and we can have high affinity ligands like siderophores, and we can have lower affinity ligands like organic matter, general organic matter. And then we have scavenging, remobilization, which I think is opposed to remineralization because it's as an abiotic ionic release of iron from the organic matter rather than or from any particles, rather than sort of a remineralization, which is when organic matter is consumed. And then we also have this orthogenic ion formation, orthogenic iron hydroxides, and that's because iron is quite insoluble in seawater, and so you get iron precipitation as ferrihydrite, essentially. And this is then polymerizes and aggregates and becomes particular orthogenic iron. So these things are all parameterized in global biogeochemical models, but they tend to be fairly descriptively parameterized, and they're constrained with empirical relationships. And so the classic one is this one, which describes the ligand binding component, which is parameterized with this log K value, which is an affinity. And generally in biogeochemical models, you have one or two of these log Ks, and that's kind of it. So it's a fairly linear relationship, doesn't consider changes in ambient environmental conditions, and it doesn't consider the enormous complexity of DOM, which, you know, could contain 600,000 different types of molecules, 10% of which can have binding properties, so can bind cations. And it doesn't consider the complexity of POM, which, you know, we even know less about than we do for DOM. So how do you represent complexity in reaction pathways? So, you know, this is what we do at the moment. On the left-hand side, we have a simple mix, maybe not 50-50, but we have two ligands with two affinities. And what we want to get to is, this is not a heterogeneous mixture. This is just a very simple mixture, and we want to get to a heterogeneous mixture. So we have to do some fancy maths, make some nice equations, and then you can come up with a distribution. This is a continuous distribution model of heterogeneous organic matter, which is called the Nicodonon model. And this is what we're going to use in this study. I think I'll come to a bit more of that. So we're going to move towards a more thermodynamically consistent approach for modeling the total iron 3 pool. So we've still got our iron pool, so it's going from dissolved iron to labile particulate iron, but now we can put some actual chemical arrows, so some double arrows that go either way to indicate equilibrium, and some single arrows to indicate sort of non-equilibrium processes, which is this orthogenic ion formation. So our DOM binding, our POM binding, is described by these equilibrium conditions. And you can note there that the lithogenic component, the refractory component, disappeared because that's not going to take part in the whole reaction pathway at all. So we're going to describe our DOM and POM binding, with the Nicodonon model. And we're going to use stability constants to look at siderophores. So these are not conditional stability constants, they're thermodynamic stability constants. And then we're going to use a solubility product to look at orthogenic ion formation. And these parameters have all been, these models have all been parameterized to varying degrees of confidence over the past 20 years or so. And some of the parameters are available in these references here. And then we need a study site, and our study site was the South Pacific Ocean geotraces cruise, which took place across roughly 30 south a couple of years ago along this transect. And because it was a geotraces cruise, we determined concentrations of iron on the cruise. In this chemical model, we use the total reactive iron pool, and this is the total labile iron. So this includes some particulate iron and all dissolved iron. And this is how the data looked across the transect. So and these are what it's made up of down here, the labile particulate iron and the dissolved iron. So for dissolved iron, we see some inputs on the eastern margin of the transect from the Peruvian shelf, and we see some inputs from hydrothermal vents in the mid-Atlantic ridge, the mid-East Pacific rise, wrong ocean. And then we see also some inputs from this volcano region on the western side of the transect. For labile particulate iron, we see a lot of input from both the East Pacific Rise and the volcanic region in the west, but not so much from the west, the eastern margins. And there's also a little bit of an input in the benthic regions as well. And then to go with our iron concentrations, we need the distributions of the key variables and reactants. So we need to have pH. So we measured DIC and alkalinity across the transect in order to derive pH. We need a quantity of DOM. So note this is dissolved organic matter in kilograms per litre. And we get this from the dissolved organic carbon concentrations and a conversion factor. We have siderophore concentrations, which we determined using solid phase extraction, followed by chromatography and mass spectrometry. And then we also need the POM, the particular organic matter concentrations, again in kilograms per litre for our chemical model. So you can see that the POM concentrations are quite a bit lower than the DOM concentrations, which is what you would expect, but that we have a little bit of a gradient of higher concentrations towards the 250 meter mark, and lower concentrations in the deep ocean. On the other hand, the siderophores, they're not, this is a stochastic occurrence of siderophores. You can't really predict where they're going to be, I don't think, very easily. And you tend to, we saw similar sorts of things to what Louis et al. Saw in the Pacific Ocean before, which is a sort of patch of siderophores in the just below, in the upper sort of 1,000 to 500 meters of the water column, which is probably related to intense remineralization of organic matter, but it's not really related to iron concentrations or DOM concentrations or POM concentrations or anything like that. So we need to have it in our models, though, in order to understand what the impact is, at this stage anyway. So just to mention how we get the POM concentrations, just looking at the time, we have, we just use the POC to total particulate phosphorus ratio, and then had a calculated the POM from assuming 50% POC by mass. Okay, so back to our model, our chemical model. So we have now we have all the variables we need to put into the model. And first of all, I'm going to show you results that relate to this iron prime, because this is what drives all these different it's what drives how much iron goes into all these different phases. So the iron prime concentrations, we can also use this to look at the impact of heterogeneity. So we could see that if we plot here the dissolved iron concentration against the iron prime concentration. So iron prime is related to dissolved iron, as it should be, and it increases. And the data here in the colored symbols are from this Nicodon model. So this is from this work. And then this crosses here are log K calculated from a sort of non-heterogeneous model. So a model that it's a simple log K and L, which was data collected from GP16, so a bit further north in the Pacific Ocean. And we can see there's a huge contrast between the two data sets. So the non-heterogeneous predictions are for iron prime are much, much lower than when we incorporate heterogeneity. And importantly, Fe prime never reaches saturation state if you don't include heterogeneity in your model. And we could check that if we plot things on a log-log plot. We can see this is the same data, it's just a log-log plot, so that you get a little bit more of an impression of the difference between the heterogeneous data, so the Nicodon model data, and this log K ligand data. And the reason is related to the log K value. So the impact of heterogeneity is that you have a much bigger range of conditional affinities that describe how much iron likes DOM, basically. And as you increase the iron concentration, of course, iron is going to like the binding sites in DOM less because they are weaker binding sites. Whereas you don't capture that if you just use these observations of log K, these conditional stability constants. Okay, so moving on to the outputs of the model. So once we have set up this model, we can predict these different phases. So we've got predicted ion bound to siderophore, predicted ion bound to DOM, predicted ion bound to particulate organic matter, and predicted orthogenic ferrihydrite or iron hydroxides. And if we add the top two together, we get a predicted dissolved ion concentration. And if we add the bottom two together, we get a predicted labile particulate ion concentration. And then we can start to compare these two with observations. So I've plotted here the observed dissolved ion, or the observations are on the x-axis, so dissolved ion, labile particulate ion, and the predictions are on the y-axis, so predicted dissolved ion, predicted labile particulate ion. The black line is the one-to-one line. So this is what a perfect model would produce. So the model isn't perfect, of course. So there's some scatter, but there's also some offset. So predicted dissolved ion is slightly higher than the observed dissolved ion concentrations. Predicted labile particulate ion is very slightly lower than the observed labile particulate concentrations. In addition, we can use an analysis of residuals to identify outliers. And so all the orange data points are kind of the inliers, according to this analysis of residuals, and all the clear data points are outliers. So then it becomes interesting to know where these outliers are. Are they just randomly scattered, or are they, in particular places? And of course, they're in particular places, otherwise it wouldn't be interesting. So first of all, we can look at where there's less predicted dissolved ion and more predicted labile particulate ion than observed. So that's in the blue areas, shaded areas on the top plot, and the red shaded areas on the bottom plot. And where we see these is near ion sources. So these are areas where you have a lot of ion input, and this is, I think, this points to zones of intense orthogenic ion formation, orthogenic ion hydroxide formation. And because this formation process is quite slow, you have a bit of time before the system reaches equilibrium, because of course our calculations are made for equilibrium conditions. So these areas are supersaturated with respect to orthogenic ion minerals. And you have kinetic control of dissolved to particular ion partitioning via colloids. So then we also have a region where we have less predicted dissolved ion and less predicted labile particulate ion than observed. And these tended to be close to the seafloor. So in these regions, we have resuspension of ion in a labile particulate ion pool does not equilibrate with the dissolved phase. And this kind of fits with an idea that this is ferromanganese particles. So these ferromanganese particles will fall into this labile particulate pool that is operationally defined during the analytical procedure for its quantification. And the ion is hydroxides. It's associated with the manganese as well. But it doesn't really dissolve. So once it's in the water, it just stays stuck to the ferromanganese particles. Okay, so going back to our controls, the original thing, what difference does it make to this overall picture? So I mentioned I was talking about this release and scavenging and the ligand concentration. So these are the three kind of terms I want to focus on that I think change as a result of this study. And what I think I learned from doing this work is that variability in affinity is essential for predicting thermodynamically consistent pathways for orthogenic ion mineral formation. So you can't get there if you can't get orthogenic ion mineral formation if you don't have this variability in affinity. So Yeah, so this is really critical for widespread orthogenic iron formation. And then I think the second thing that comes from that is that iron losses in the ocean are mainly driven by orthogenic iron formation or iron mineral formation. And that happens proximal to iron sources. So the main losses are not, they're occurring in localized regions around iron sources. And of course, that's why iron concentrations are quite low everywhere in the ocean. And then the release part, I think, is also, it's not really a release, it's an exchange. So maybe it can be described by a chemical equilibria between dissolved iron or between Fe prime actually and POM binding sites. It could also be surface adsorption or desorption on other types of mineral particles, which we didn't have to consider in this region because they just weren't very abundant, things like carbonates or silicates. So those are the three things that I think change, and the overall impact I think is on how we where iron is lost in the ocean and how that might change going forward as sources change, as conditions in the ocean change, and overall getting a sort of a better handle on these processes and how we can describe them in a less empirical and more thermodynamic way is, I think, pretty helpful for our understanding of iron biogeochemistry. Okay, so that's I think nearly good timing. And I'd like to thank everybody who was on the cruise who helped with all the sampling collection, especially Leah Bloom who did the siderophore sample collection and everything, but also Katie and the guys who did the DIC and alkalinity analysis and everything. And also my colleagues Pablo and Carlos Rey Castro, who are at Yale University and who really helped me with the Nicodonan model and conceptualizing this heterogeneity of organic matter. So thank you.
Excellent. Thank you very much, Martha. Yeah, iron chemistry. I'm constantly impressed by people disentangling it. So let's hand over to anybody who has any questions. I see that the audience has grown during your talk, which is great to see. If anybody has a question for Martha, then please just put your hand up or open your mic and ask a question. If you want to, feel free to type it into the chat and I can read it out, whichever you prefer. Toby.
Hello,
Hi,
Adrian.
Toby.
Hello, Martha. Thanks very
Good to
much
see
for
you.
that. It was really interesting. I've probably got what's a fairly typical modeler's question, sort of trying to understand it without being able to get the handle on all of the complex chemistry. But I suppose what I'm really interested in is what sets the deep ocean concentration generally. And I've sort of had a picture in my mind for a long time that it's scavenging by particles, that if you have more iron, dissolved iron, it sticks to particles in some such way and gets removed from the ocean. Do I understand it right that your new work agrees with that, but with the caveat that it's mainly through production of orthogenic iron hydroxides specifically? Would that be a correct statement?
I think that is a correct a correct inference to draw from the work. Yes, I think so. Going into this work, so there was some work in the early 90s from Balistrieri who really looked at the affinities, surface adsorption processes. So if we think about, iron sticking to particles, that's surface adsorption. For minerals and for organic matter, it's binding essentially. And I think you can't get there. You cannot get enough iron loss through those processes. Basically, the affinities are just not high enough. The surface adsorption is just not a high enough. Yeah, it just doesn't do the job. From the measurements, the proper measurements that have been made of these processes, and nobody's done this since the early 90s. So it's kind of something that happened a bit and then nobody did it anymore. And so we really lack understanding of those processes, I think. But at the moment, I'd say the indications are that that's just not gonna, do the thing it needs to do. So the only way to get rid of all the iron is by this orthogenic iron production, and that is determined by basically the equilibrium between DOM and Fe prime. So this is a DOM controlled process, really.
Does it mean that the removal of iron as soon as it starts to reach a high concentration is not dependent on the particle flux?
Correct.
Okay.
It's an independent process, creates particles.
So basically, even if you have no particle flux, as long as you've got a big source of iron into the ocean, absorbed iron, you'll remove it through this formation of this mineral.
Yeah.
These minerals. Yeah.
Yeah.
Oh, that's really interesting. Yeah.
I think so. Yeah. That's kind of my understanding based on this study. Yes.
Okay, we'll have to revise the paper we've got.
Yay!
Yeah, that's great. Thank you very much. Anyway.
Yeah.
Excellent. Thank you for the question,
Thanks,
Toby.
Toby. Yeah.
I think we've still got time for another question if anybody has anything that they want to ask. So either type it into the chat or put your hand up. Otherwise, this seems unfair, Martha, because you said it at the start, but I have to ask, how do things change if you do have a lot of respiration in the interior?
I don't think it really makes. So in actual fact, to our calculations, it doesn't really make all that much difference because we based our calculations on observed POM abundance. Inferred observed POM abundance, which is quite consistent with what you would with observations in other places. So it's not kind of like we've invented some weird numbers which don't match observations in other places. There really is that much POM. So I think in actual fact, respiration or DOM as well, it's based on the DOC concentrations. They don't really change all that much in the deep ocean. So what respiration could change a little bit is maybe a bit of change the pH a bit, but again, that's something that we parameterize in the model, so we know what a pH is. We make the calculations based on that. So I don't actually think I mean, it would matter in a biogeochemical model, but it doesn't matter for our calculations.
Some things for the model is to worry about.